All right. Hi, everyone. Thanks for joining us this morning, bright and early at 8 a.m. My name is Darryl Daniel. I'm a mechanical engineer with Meta on the hardware platform team, and I'm joined today by my coworker, Wenying Zhang from the thermal team, also with Meta. And today we're going to be giving some updates on some follow-on investigations to the ORv3 blind mate liquid cooling track. So these are some things that came up throughout the development cycle, different pieces of feedback that we received from the OCP community as we were kind of working through the BMQC designs. So we're just going to give some updates on some of those different work streams. The three areas of focus today are going to be alternate hose routing within, and this is focused specifically within the IT gear chassis. We're going to talk a little bit about EPDM hose investigations. So with the specs that were released this past summer, the vast majority of that testing was done with the PTFE convoluted tubing. So there's an interest in using EPDM hose as well. And then finally, we'll go into some investigations around a 10U pitch on the manifolds. So in the reference design that we released this summer, we had 12 chassis within the rack, and those were 30U chassis. And so the pitch of the valves themselves was a little bit larger than 10U, but we understand there's a strong desire within the community to have a 10U chassis in the rack. So we did some further investigations around that as well. So starting off with alternate hose routing. So various internal chassis hose routing scenarios were studied by the group, and this was based on different industry trends. There's a lot of work going on in liquid cooling right now, lots of development within the IT gear, and so just different things that we've seen different companies working on. So we did some further explorations on some of those different hose routing scenarios. We also had strong ask from different OCP community members to consider hose connections or routing that was very close to the back of the plug within the IT gear chassis, where that barb connection happens, and making a sort of quick turn from that. And so with that in mind, the valve vendors tested lots of different hose configurations with all the different combinations of valves. So Nick mentioned, there was 16 different combinations between the different valve vendors that were tested. So this was done with those in mind. And so some of the different lessons learned from this are, sort of fairly obvious, right? So the more length in the hose that you have, the more ability that hose has to flex and not necessarily influence the valve itself, right? These are floating valves, so any force that you put on them can cause some bias on that. Next, with a short right angle connection, which uses a hose guide within the chassis to kind of guide the hose into the back of that barb, it performs reasonably well. And then sort of as expected, right, as you go to a shorter, tighter bend with no hose guide, it's prone to excessive mate forces and binding. And so the way that we sort of characterize this when we were doing our test setups is we were measuring that mate force and doing the mate cycling testing to gather this data specifically. So this is just a sort of diagram of those three scenarios that I was talking about. So if we start on the bottom, you have the long hose. Obviously, there's room for that hose to deflect, and so it produces less bias on the valve itself. On the top left, when you have a hose guide involved, it can help sort of straighten that hose out as it enters the back of the plug. And again, it helps reduce the amount of forces that are being induced on the plug itself. And then in the top right picture, when you don't have that hose guide, you have that tight bend coming off the hose. It can put some additional forces directly onto that valve, and so that's when you get a little bit worse performance from that. So with all this in mind, we are still doing some further investigations on this, and we'll be providing some additional updates to the community later. But this is one of the work streams that we're pursuing currently. The next area that we kind of focused on is EPDM hose investigation. And really this was a piece of feedback that we received from the community, that there's a strong desire to use EPDM in some scenarios. And then there's also some, looking ahead at different future regulations on PFAs. I mentioned earlier, the initial specs that were released were done with PTFE convoluted tubing. So this is one of the work streams that we were also looking into. Within the group, there's some hose manufacturers that we worked with to develop a thinner, more flexible EPDM hose with specific chemical compositions that work with the coolants with these types of systems. Another piece of strong request from the community is that the connection to the plugs themselves, there's a strong desire to have a push-on style connection to the barbs, which doesn't require a hose clamp, which, the clamps take up additional space and can create some sharp edges depending on the type of clamp used. So with this, the new EPDM products that were developed through the different vendors within the group are currently undergoing additional validation testing. And this will be happening both at just the hose level and then at sort of the combined hose and valve level. So some of those initial tests include burst tests, impulse, creep, halt, and permeation. All right, and now I'm going to hand it over to Wenying. She's going to go through some of the thermal efforts that we've been doing as well.
Okay. Yeah, thank you, Darryl. So in the next session, this is about the 1OU BMQC study using 1D flow network modeling. So the background is here. So we want to understand the feasibility of BMQC 1OU study from the thermal or hydraulic perspective. So we are utilizing the 1D simulation method and existing data to first validate our simulation methodology. And then we want to do some sensitivity study and understand how we can achieve the BMQC 1OU pitch. So there are some physical limitations in this study, and there are some parameters we were using. The first is similar to the previous presentation. We want to maximize the BMQC flow range, which is roughly 9 LPM. And also we want to explore the reasonable L10 pressure drop range for future liquid cooling platforms. Third one is we were exploring the single inlet versus straw inlets on the manifold. And also, for now, we are using the L11 pressure drop limitation to be 20 to 25 psi. And the last is we want to maintain the flow distribution among all the 36 different BMQC chassis within certain range. So the definition is the maximum flow rate minus the minima divided by the average. So across the whole manifold, this should be falling 5 to 10%. So we started with validating our simulation methodology using the existing test data. Thanks to our manifold supplier, they helped us to do the manifold flow and pressure drop testing. So on the right-hand side, you can see there's a chart comparing the test data versus our simulation. Simulation is a blue line, and the error is within 8%. So after we validated this simulation methodology, we built our baseline model using 1D microflow simulation. And here are the baseline model setting. So we use blended manifold, of course, with 36 1OU design. For the manifold itself, the spiral tube, it has 25 millimeter internal diameter. And for the manifold itself, we have 40 times 40 millimeter square cross-sectional area. For the large QD, we were using 1-inch OCP large QD average performance. And there are certain extrapolation from the 120 to 160 LPM. We were also using 5 millimeter BMQC average PQ performance. And in the baseline, we use a certain reference L10 pressure drop design without any QD. There's no L11 hose included in this simulation, and we use Dow-Frost LC25 property at 45 degrees C. There's only one inlet or outlet on the manifold for the baseline model. And then with the baseline model, we continue with the sensitivity study. The first step is the manifold dips. So we were changing the dips from original 40 to 65 and 90 millimeter. So the conclusions you can see is with a deeper manifold, it helps to improve the flow variation from among the 36 chassis in the rack. So looking at the chart, the orange dots are with the 40 millimeter deep manifold, and you can see the blue line improves this flow variation. However, the improvement gets marginal when you already have a 65 millimeter dips. The second parameter is the L10 pressure drop. So this is without QD. we use the reference L10 pressure drop and change it from 50% to 100, 150, and 200% of the original reference design. And the conclusion is, if you look at this chart, so basically assuming we are looking at the yellow horizontal dashed line, current manifold design can support up to 150 LPM for the L11 flow rate. So that's the, assuming we have 50% of the original reference L10 pressure drop. So that's a green line crossing the yellow line. However, if we increase the L10 reference dP to 200%, which means double the L10 dP, the current manifold can only support 120 LPM. So that's how important it is to control the L10 dP and supporting more dense design. The third one is a single versus draw inlets on the manifold. So again, as we can see on the chart, the draw inlets can help reduce the L11 dP significantly because of the QD and also the dP in the manifold. It also helps reduce the flow variation by 5%. That's a comparison from this brown dots versus the green dots. So with all the conclusion in mind, now we are going to make our recommendation. So how we can maximize in the 1OU flow rate? So we need to make certain design change from the original baseline. The first is we need a deeper manifold. And we want to reduce the reference L10 dP all the way to 30%. And we need to have draw inlets, outlets on the manifold. There's one more thing we need to mention. We want to assume there's no fractional loss from the L11 host to the manifold cross-sectional area, assuming there's a certain customized design which can reduce the fractional loss to the minimum value. The last is we want to increase L11 dP limitation from 20 psi to 25 psi. So without the design change above, we can guarantee the current blendmate 1OU manifold design can support up to 290 LPM for the L11, which means 8 LPM per blendmate QC. I will give it back to Darryl.
All right, thank you, Wenying. So kind of continuing the discussion for 1OU pitch investigations, there's some physical implementations that we also had to evaluate for feasibility. So the first one was the manifold manufacturing based on a 1OU pitch. So within the group, we performed some manufacturing studies and we created some different prototypes of this. And really the purpose of that was to be able to verify that the tolerances that we specified in the blindmate manifold specification could be achieved with this tighter pitch of ports on the manifold. So as you add more ports, due to the manufacturing processes, you're typically adding more heat into the tube during those processes, and you need to manage that. So we wanted to verify that that was achievable. So the reference design with the 1OU pitch that we used, as Wenying mentioned from her flow modeling, we used 36 ports at a 1OU pitch. We did have a cross brace at OU position 23, which is roughly in the center of the manifold design, and that was using the blindmate liquid cooling kit that was developed previously. Currently, first article inspections are ongoing for those prototype samples that were created. Preliminary results from one of the suppliers suggest that those tolerances are achievable, no issues there, and we're still awaiting results from the second supplier. But so far, the results look very promising, and it looks like this is something that can be dialed in through manufacturing processes. Obviously, the next thing we had to look at was the chassis itself, right? So the IT gear, we're going down to 1OU size on this. So with that, we created this reference chassis design. We performed some FEA analysis on it. But the first thing that we noticed is with the float of the plugs and the housings in the back, there's a centering feature in that has a sort of a retaining ring on it. And because of the float of that, there's this 43 millimeter keep-in zone that we had to maintain. So we added a couple of slots in the chassis just to allow that full float range of the centering feature. And it doesn't extend beyond the chassis, but we did need that cutout added just to allow that full range of motion. Second thing that we looked at was from like an analysis standpoint with FEA, We increased the pressures from 35 to 50 psi for the valves. And so we wanted to look at the mounting features within the chassis, the bracket specifically, and the surrounding structure in that chassis, just to make sure with that added pressure and the smaller form factor that we were still within the displacement and stress limits of those components. And so the outcome of that analysis is that we were able to verify that with that 1OU chassis design, we are still within the IT gear design limits. Oops, skipped ahead. All right, next area that we looked at within the chassis itself is some of the hose clearances. So as you can imagine with the float on the plugs, as they do move around, the hose moves with them. And so we wanted to make sure that the 1OU chassis design wasn't going to limit or constrain the movement of the hose and impact the mate force of those valves. So we used fixtures, and we did use the PTFE convoluted tubing to evaluate that hose movement within the 1OU chassis design. In addition, we included, we were looking at the worst case blind mate quick connect skew within the zones in the chassis, and we defined this minimum keep end zone. And sort of the result of this overall investigation is that the 1OU chassis height can be accommodated with BMQC with no interferences to the chassis walls. All right, and sort of the last part of this analysis was looking at both the manifold individually and looking at the system as a whole in terms of the strength and deflection that we see, given that we're going from 24 ports in the original reference design to 36 ports at 50 psi with the updated. So starting off, when we look at the manifold only, we look at sort of stresses and deflections, and overall that looked very good. Everything was well within the yield stresses or yield strength of the material itself for the tubes, so no concerns on the manifold side. When we did the FEA at the system level, so that's adding the rack into the design and the mounting structures, we did find that there are some displacements at the manifold port. So that's one of the things that we looked at is the displacement at the tip of the port. And from that, we did see that some of those displacements did exceed the design slightly, as well as some specific discrete locations within the rack from a stress level exceeded the yield strength of some of those components. So what that tells us is that there's a little bit of additional work that needs to be done on some of the rack side components in order to fully support a 1OU design. Some possible ways to address that are to add additional web stiffeners. So we didn't increase that from the original reference design that was released this summer to the 1OU investigation. We still used 4 of those web stiffeners on each side. We could easily increase the number of those. That adds more stiffness to the front of the rack where the injectors from the IT gear are pushing on. Another thing we could look into is stiffening the mounting brackets. So when we did that system level analysis, we noticed there was actually a lot of deflection on the manifolds, but it was resulting from some of the displacements in the brackets specifically at the top and the bottom of the rack. So we could increase the material thickness of those brackets. We could go to a stronger steel for those to potentially counteract some of that. And then finally, another option is to add additional bracing beyond what's already specified in the blind mate liquid cooling kit. So for that, maybe putting something behind the manifold to help counteract the force of all those valves. So those are some of the things that we looked at. We didn't go so far as to actually develop all of those different solutions. That's really going to be up to the community to kind of do the final design on those and validate their own designs. All right, so that's what we have for the updates. If anyone's interested in learning more about this or any of the other work streams here, definitely scan the QR codes, join the mailing lists, get involved, and that's it. I think we may have a minute for time, about 1 minute for if there's any questions on this.
Paul Arbor from AMD. Quick question. A good analysis on the manifold depth and outlets. Do you have any data that kind of has the whole loop resistance, meaning what's the cold plate, QDs, manifold, outlet, the contributions of all those subcomponents, and then what are the assumptions on the loop? We're seeing a lot of QDs on the loops themselves, which adds pressure up, and you start, and 25 PSI is pretty high.
Yeah, We do have the data, and if you are interested in, we can talk more about the component distribution. But in terms of the small QD, are you asking for the small QD numbers in this model?
I'm just trying to send the assumption on your loop. So your liquid loop is going to go into your blind mates on your manifold, and you're making a lot of 20. You're trying to stay within 25 psi.
Yeah, for the whole rack.
Trying to understand it. On the loop itself, what we see a lot of times is you have the QD, blind mate QD, and then a lot of times you actually see hand mate QDs for serviceability. So just trying to understand that pressure drop of that subsystem you're assuming and you're modeling versus what you're seeing at the L11.
Yeah. I think the major reason of this high L11 QD is, L11 DP is because of the high flow rate. But of course, the contribution of each component matters. I don't think the blend QC is a major contributor. Yeah,
Okay.
just for your information.
Well, thanks.
All right, thank you, everyone. We're out of time. We'll hand it over to the next group. Thank you.